Zero-point energy. It's an established fact in physics that vacuum is not empty. When all matter and radiations are removed from a system, the system still contains energy and vibration. That's called zero-point energy. The fact that vacuum contains zero energy was shown in Casimir effect experiments. Casimir observed that two closely spaced very small mirrors or metal plates with no electric charge in vacuum attract each other. Why? On the picture, the waves represent the vibrations in vacuum. The waves between the plates are restricted to certain wavelength and therefore a certain amount of energy, unlike the outside waves that are freely acquiring wavelengths and thus more energy to push the plates toward each other. Henry Casimir first encountered this phenomena in his calculations in the early 1930s with the help of Niels Bohr. At a time, he speculated that the mirrors attract due to zero-point energy. In 1948, however, the Casimir effect was experimentally verified. We call it zero-point energy because it refers to the energy of the system at absolute zero or 0 degree Kelvin, which is about negative 273 degrees Celsius. According to the classical mechanics, the energy of the system at absolute zero should literally be zero because all motions stop. But we now know that this is not the case. Lastly, it's very important to mention the Heisenberg uncertainty principle because zero-point energy can be directly derived from this principle. The principle states that we cannot simultaneously determine two closely related phenomena like position and velocity with precision because any system inherently has some minimum amount of uncertainty. So, if you try to pinpoint a particle's position or decrease its uncertainty, its vibration will vary significantly, and vice versa. If you try to measure its velocity or frequency, the uncertainty in its position will increase. Therefore, both scenarios imply ceaseless motion and energy everywhere at all times.